Welcome to the Bachelor in Economics Management and Computer Science. Thank you all for being here. I'm happy to introduce you to this new Bachelor program of Bocconi University. I am Emanuele Borgonovo and I am the course director. The moment that we are living nowadays is called the data-driven economy. We all know that globalization is driving and is changing our lives, is changing the way in which we interact with other people, with the emergence, for instance, of social networks. And even the current situation with the pandemic has accelerated the process of communicating through a distance. We are becoming more and more digital. This means that humanity is releasing an enormous amount of information on the internet and on the web. This information is growing exponentially and creates opportunities for improving decision making and also for business. There is a disruption with some activities that unfortunately are becoming old, but however, there are many new opportunities and activities that are opening. And this may make a difference, especially for the career of young students starting a university program. What is big data? Big data is data that have three main characteristics. They are high volume, high velocity, high variety. What does it mean? For instance, variety means that they can be images, they can be audios, so not necessarily tables with numbers. And then, of course, to process this data, what you need to do is to transform them into numbers through appropriate algorithms. Variety, so we have said the volume, which means very high amounts of data, and we can start talking about with big data when the files that you're opening and that contain the information you're looking for cannot be stored on your computer. Then the difficulty is that how do we store all this information together? So what has enabled the use of big data are some technological breakthrough and the fact that in informatics, informatical engineers have been able to gather data from different sources, bring them, let's say, in a cloud or in a common platform, and then software has been developed for us to be able to go to this platform, which is no more on a given computer, and open with dedicated software very large data sets or very large amount of data. What happens if the data are not big? Well, it means that the data stay on your PC. But once you have opened, let's say, the data on your PC or on cloud or with some particular software that allows you to open very big data, the point comes to analyze the data, to extract information that is within this data. So from that perspective, having data on your PC or having data in a cloud is, in a sense, conceptually quote unquote the same. Technically it's different because we need different infrastructures, but then technically the question is, how do I use this information? And this is the purpose of the university education of the Bachelor in Economics Management and Computer Science, to develop the critical thinking for using data, being them big data or small data. Here is a slide that tells you how many data are charged by humanity, and you can see the growth is exponential. The growth in the amount of data that humanity generates is exponential. At the same time, it is exponential also the growth in, at the moment, the look for competencies in this area. Currently, data scientists or economists or managers who can use data science are in high demand. And the perspectives for the next 10 years, or let's say the next 5 years, look the same. So we have no hint, no idea that this type of professional figures will be less in demand in a few years with respect to now. In a few years, we will update our view, but at the moment, there are still professional figures in high demand. And as said, tragically and unfortunately, the situation where we live has really accelerated several processes of digitalization, of smart working, of using digital information that so makes these figures even more in demand. How can we use big data? I am going to tell you some story about the beginning of how all this happened. Consider that you are in year 2008, so now it's 12 years ago. And in 2008, the municipality of New York, with the Mayor Bloomberg, decided to open the first, let's say, data office of a town, actually the first data office, official data office of a city or a state that we know. Bloomberg is an entrepreneur who has made success in selling data in the financial sector. So he probably understood the importance of data all along. And in 2008, he called a statistician or a tactician of the US Army, Mike Powell, and gave him the role of first chief data officer of the New York City. Now, the role of Mike Powell was that of gathering data from New York and using this data to improve decision-making, to make suggestions to the mayor or to anyone else of the New York municipality who would ask him for advice. The first application that is recalled is on fire, so safety. In fact, there is a problem of fires in several cities, and of course, fires put in danger not only the lives of the ones who are in the apartments or the houses, but also of the fire workers, and potentially it's a safety issue that impacts several lives. In New York, you had 900,000 buildings and 200 inspectors. So the number of people who were going to check for the safety of buildings versus the number of buildings to be inspected was disproportionate. Also, the efficiency with which buildings were inspected was insufficient. In fact, for the inspection successful rate, the success rate of inspections was only 13%. It means that every 100 visits, only 13 times on average, you would find buildings that actually were to be inspected. So it was needed to improve this efficacy. Okay, so the success rate would have to go from 13% to something more. And this was the problem that the team of data scientists working with Mike Flowers actually addressed for the first time. So what they did, they gathered together various information sources, various data sets that were not only in the office of the New York municipality, but maybe some data sets were of the police, some data sets were of the tax offices, because they wanted to understand a bit how buildings were made and find those key variables that could characterize a building as an outlier. So this building, because it has the values of these key variables, is not a normal building. We better go and explore it. This is technically called cluster analysis. Then they made their suggestions and they highlighted the buildings that were not quote unquote normal or not regular. With the quantitative analysis results, they went to the inspectors and gave them their suggestion. They would say, well, I think we should visit this and this and this and this building. And in fact, the efficacy of the inspections went from 13% to 70%. So a huge increase in the efficacy of decision-making thanks to using quantitative information. Not only to using quantitative information, but to using quantitative information well, that is, having good data and using the appropriate algorithm that allows one to take out the information that one needs from the data. There are several other applications in revenue management, for instance, in online sales. So with the computer, there is a lot of information about the behavior of people, what they appreciate as so the right price for a t-shirt, for instance, and the computer can learn from this behavior of people that are online and participate to online auctions. And in fact, there have been cases in which using the algorithms, the sales have increased by 400%. If you read this list, you see several other early applications of big data and algorithms, but now they are even more diffuse. The European Commission, about 6 years ago, in 2014, which is about when we at Bocconi started building this Bachelor in Economics Management and Computer Science, issued a communication of the European Community to the European Parliament, so a study on the data-driven economy. The study has in its conclusions that we need the training of professionals who can perform in-depth thematic analysis, exploit machine findings, derive insight from data, use them for improved decision-making. This is, in a nutshell, what we illustrated before with the fire safety in New York application, right? So we need professionals who can use data. Machine findings in this case means results from algorithm or numerical processing of the data to communicate to decision makers and allow them to make better decisions. In fact, nowadays, the decision-making process is becoming different than in the past. In the past, you could rely more on intuition. So you had a real-world decision problem, you relied on intuition, you brainstormed, made a lot of reflections, and then you decided. Now we go more through try and have data, quantitative information, develop a model, so an algorithm that analyzes the data, perform the analysis, consider the results, and then make a decision. This second route is the one that is becoming more and more popular through the presence of big data or just data. By the way, humanity is using data and numbers since the time they could do that. And there are firms specialized in statistics and data science since several years. So not only from 2008 up to now, but the awareness, the availability of such a quantity of data has created the awareness that these data are important. In fact, several people are calling them the oil of our century. And so it's important to be able to understand and exploit the information that is hidden in the data. Note that data by themselves don't help anyone, because having data on a computer and not looking at them, not analyzing them, not processing them, makes their value null. Even before, the data-driven economy, people were aware of the importance of using computers to process data and information. Here is a quote from Friedrich Smith, the CEO and founder of FedEx, who says that using computer simulations actually has helped FedEx in making mistakes on paper. If you can create a virtual reality, a good forecast of what could be the future for the problem you're looking at, of course, limited, you cannot make a model of the entire world. Just for the problem that you have, you can create good predictions. This helps you in orienting your decisions without having to actually carry out maybe even the decision in the field, which is going to be much more costly than just doing numerical experiments. One ingredient in all this story is algorithms, Actually, we have three main ingredients. Computing power, the fact that our computers are now much more powerful than what computers used to be. Huge amount of data, technology for store this data, and algorithms. So algorithms are the third pillar of the data-driven economy. But algorithms are not perfect. Several of the things that we do is called artificial intelligence. That is, if you are able to write a good program that has several algorithms, combine them together, you actually can create even a robot that executes very complicated tasks, And then it seems that it is artificial intelligence, but this artificial intelligence is just a stratified overlap of human intelligence, In each bit of that process, there has been the work of a human who has done a little bit of a code, a little bit of an algorithm, or an entire algorithm has envisioned a new way to do something on the PC, But it's human intelligence transferred into the PC that plays the role of amplifying our calculus capabilities. In the case of Google Flu, however, the algorithm didn't work, but that's exactly why we know that. We know that because it has been made by humans, and humans can be wrong, So an algorithm, an artificial intelligence, is still a product of human work, So as we can be wrong in building a table, we can be wrong in building an algorithm. We will need skills of people who analyze the algorithm and understand, maybe after a lot of work, what's wrong in that algorithm. Here is a case. Google had the nice idea of saying, let's try and find a way to predict influenza, the spreading of influenza, or the influenza disease, which is similar to COVID, from researches in Google. That is, if people in the province of Milan digit headache, antibiotics, high temperature, and all the other symptoms, then maybe there is a lot of people who are getting these symptoms at the moment in Milan. And if we see that the number of researches is increasing of the same type in the province of Bergamo, then maybe we are likely to have the flu that goes from Milan to Bergamo. And knowing that it is going to Bergamo could create an alert, could maybe have the authorities that suggest some quarantine measures, or lockdown, or other. Okay, it could help a lot to have this early forecast. Now, Google did that using the searches. They actually produced results better than traditional models up to 2010, 11, and 14. In 2015, or 14, so one of these years, their model was really a disaster, and it performed much worse than traditional methods that were used before this intuition. What is the cause? We actually don't know. Maybe it was due to overfitting. Maybe it was due to the fact that the searches, the Google searches were unreliable that year. So even if you had the search, it didn't mean that this search was actually related to the flu. And then Google abandoned the initiative. If you look at the website, if you Google flu, we see that they abandoned it, and we don't know actually why, if someone else has continued or not. Well, to adjust the algorithm, we would have to know the reason why, okay, the algorithm failed to produce efficient results. And this requires someone who knows the problem, knows the algorithm, knows the statistics that was used to make these calculations, and then can find the reason of an error, or the reason why maybe this category of algorithm is not appropriate, and one should use a new type of algorithm. An example is offered by the so-called Vals brains, okay, that transmit us this idea of critical thinking. Abraham Wald was a statistician, one of the greatest statisticians of the past century, and was called by the US military, actually the US Navy, to help them solving a problem during the Second World War. And the idea was to support the decision-making to increase the probability that planes would come back safely from the battlefield, or successfully from the battlefield. What Vals did was he went on the ships, and actually he organized a team to gather data. Imagine that the gathering of the data was done in the following way. You had a plane that was not hit, so it was completely safe before starting for the mission, and then for every plane that came back, you would register with the black dot the position where the plane was potentially hit. After gathering the data, having a sufficient amount of information, Vals performed complex, I would say quite articulate calculations to give his final decision to the military. The moment in which he reported this to the engineer or the commander that would ask him this information, he showed this picture, and the engineer had the reaction of, okay, so let's reinforce all the parts that we see are black here. And the answer of Wald was, be careful, because the planes that we have observed are planes that actually made it back from the battlefield. We don't know anything about the planes that actually are on the battlefield. So in fact, if you see, the parts that have not been recorded as hit here are the ones where we have the pilot, or this back wing where there is much of the control of the stability of the plane. So maybe we should do something on these two parts, okay, instead of the other parts, because the other parts still were parts that allowed pilots to come back from the mission. But what is the idea? The idea is that maybe an intuition that we have is not immediate or not enough, because we have to have critical thinking. The problem that Wald, in this case, highlights is called sample bias. That is, if you are observing, this is even famous risk analysis. We observed, for instance, in Europe, that swans are all white. Okay, we have never seen in Europe a black swan. So if we come to the conclusion that swans are all white, we would be wrong, because we have never observed the black swan that people then observe in Australia. And so now we know that swans are both white and black. The point is, if I make inference only on white swans, I need to say in my hypothesis, look, I'm reasoning on white swans. I cannot extend these conclusions on the entire population of swans, because I'm not counting for the black swans. And here is the same. I'm reasoning on planes that came back. This is my evidence. I don't know anything about the planes that were not, unfortunately, successful. And this creates what is called sample bias. That is, my data are giving me only part of the information. So in my calculations, I need to account for the potential states of the world that are not visible in the data. These, of course, create nice and challenging mathematical and statistical problems. So humanity, as I was saying before, started using numbers since its early times. And here we have an example of Eratosthenes of Cyrene, who produced one of the first algorithms. Eratosthenes was a scientist born in 276 before Christ. So if you add it to 220, we are talking about 2,300 years ago. He was the librarian of Alexandria in Egypt, and actually he was capable of computing the circumference of the Earth and also the inclination of the axis of the Earth at his age, without having any map or any Google satellite image. So this tells you, something about the marvelous things that our human mind can do. Again, artificial intelligence is just an overlap of several layers of human intelligence. What is Eratosthenes famous also for is one of the first algorithms in history. An algorithm is a series of instructions that if you repeat them, they lead you from the initial point where you are to a final calculation, a final outcome of interest. And if you repeat them identically, they will always produce the same result, at least if they are deterministic. Maybe they have some variability, they are stochastic. But in this case, we have a deterministic algorithm, and he wanted to find prime numbers. Now, what is a prime number? We know that a prime number is a number such that I have to take that number, divide it for the numbers that are before it. And if none of these divisions gives rise to an integer, this integer number is prime. Okay, so if I divide 10 by 9, there is no round division, then I have a prime number. 10 is not a prime number because if I divide it by 5, I get 2 times 5, and therefore 10 is not prime. 7 is prime because if I divide it by any number that is before 7, I cannot get a round, okay, an integer, a natural number out of it. Actually, we should not count for 1 because 1 is sort of a neutral number for division. So we start from 2. Look, if we use this brute force definition of prime number, we have to do many operations to determine what is, if that number is prime or not. And if I have to repeat it for several numbers, the computers will do a lot of calculations. For instance, take 7. To determine whether 7 is prime, I would have to divide by 6, 5, 4, 3, and 2. So I have to do 5 divisions for the number 7. For number 8, I have to do 6 divisions, which means that if I started at 7, I have done 5, plus 8 is already, plus 6 is 11 divisions. Then you go on like that. So add another plus 1 or plus, I was 5, 6, then add 7 if I want 9, then I add 8 if I want 10, and so on and so forth. And this continuous addition of increasing numbers makes it easy that, for 20, probably you're already above 100 divisions to be done to determine whether 20 is a prime number or not. Okay, which is, imagine you want to find the first 1 million number, this becomes very long, very tedious. The computers will take forever to do these calculations. Well, Eratosthenes found another algorithm, and we see with a lot of less operations, we will determine whether a number is prime or not. What did he do? He said, let's start from 2 and add 2 after that. So we do 2, 4, 6, 8, 10, 12, continue like that till 20. And so we have done how many operations? 1, 2, 3, 4, 5, 6, 7, 8, let's say 9. With 9 calculations, we already have eliminated a lot of numbers, and we found a restricted number of numbers that, on which to repeat the operation. Then we do this starting from 3. 6 we already repeated, 9, so this is another 2 calculations, and then we have another calculation here, another one, so we have done 1, 2, 3, 4, 5 steps, okay, plus the ones before. You see we have 10 steps and we are done, because all the other numbers are going not to be prime, so all the other numbers are going to be prime. So with a much smaller number than following the definition, we found what we wanted to compute. What does it mean? It means that algorithms, to be powerful, they have to be also clever. Sometimes I need to have a reasoning that goes beyond the definition. I have a mathematical definition, I want to compute that, maybe there is a quicker way to compute that than just following the definition. okay? And having quick algorithm is the essence of being able to process great amount of data efficiently and fast. Google gives you your answers in less than 0.2 seconds, because 0.2, more than 0.2 would be perceived as slow. So less than 0.2 seconds, searching millions of web pages, which means a very fast algorithm. There is some other decision support, but we don't have time to go through. How do we see all this data science, okay, data-driven economy in Bocconi? We see it as the intersection of artificial intelligence, computer science, or computer's ability, mathematics, statistics, plus management and economics. So here are our pillars. Quantitative tools, so lots of mathematics, computer science, which are necessary to process data. They are necessary to have the quantitative skills that allow you to understand what is inside an algorithm. Even if you are a manager, if you know how your algorithm works, you can use it better because you are more informed, can use it for better decision making. It's like being a pilot of an F1 car. You don't need to be a mechanic that actually builds that algorithm, but if you want to be that, our degree will allow you also to do that, okay? But suppose you want to be more of a manager, but you want to use this data, then if you know how the engine works, you'll be also a better pilot. We integrate the amount of mathematics and statistics, which I said is relevant in BMAX, with the problems in economics and management. So we apply the mathematics that we explained to economics and managerial problems. Let's see how the program is done. The program follows the structure of all other Bocconi courses in the sense that the first year is sort of the common ground, tries to take all students and bring them together, gives them, the same basis. The second year is more specialized on the subjects that we want for data scientists. And the third year is a year in which you can choose subjects that you like and tailor your preparation also even more towards your tastes or toward the subject, the type of profession you would like to do in the future. In the first year, you study microeconomics in a more quantitative and mathematical way that what is done traditionally at other Bocconi courses. You will have a first course in mathematics and a course that introduces you to the principles of management. In the second year, you will have another course in mathematics, a course in computer science. This is a blend of theory and programming because there is a lot of mathematical theory behind coding. So you will study a bit of mathematics, a ton of mathematics, and a ton of programming, accounting, and law, which is specifically designed for the data-driven economy. So it's not just a generic course in law. Of course, there are the bases, but then the specifics and the applications are for students of the data-driven economy. And this allows you to have a 360-degree vision of the problem, okay, from the mathematical aspects to the legal aspects. In year 2, we have a second course in mathematics, macroeconomics, fundamentals of computer programming, a second course in theory and applications of coding, another course in law. You see, it's International Information Law, European. Technological innovation seminars, we have 2 in the second year, and they are special for BMAX students. In the first technological innovation seminar, we are going to interact with IBM. Actually, traditionally, it's 2 companies that are at the forefront of the data-driven economy. One is IBM and the other is Microsoft. This year with IBM, we had the quantum computing seminar. In Microsoft, we are probably going to go and see virtual reality. Then you have other courses, which are advances in advanced mathematics 2. So this is a course in stochastic programming and machine learning. Machine learning is let's say, one of the few programs that you can see internationally that offers machine learning already in the second year of the second semester of the second year of university. Taking this course so early means being upfront with respect to several other programs and with respect to the most advanced even. So to be well prepared also for quantitative programs, Master of Sciences following BMAX. By the way, Bocconi has a dedicated Master of Science programs in data science that is the natural continuation for BMAX students. Then you have principle of finance and a second foreign language. In the third year, you have a course which is big data and business analytics, 2 courses, computational microeconomics 1 and 2, which are in mathematical economics at the interfaces between economics and computer science. Actually, mechanism design is really the field in which nowadays there is more research at the intercept between, more overlapping between computer science and economics. Think, for instance, of building an auction for the web, for eBay. This is the type of course that gives you the economic principle to solve such problems. Year 3, you have the possibility of choosing 3 electives. Among the 100 electives offered from Bocconi University, we have special ones like theoretical computer science. We have a new one, which is called Big Data for Business Analytics in cooperation with Siemens, that talks also about Industry 4.0. We have also some, so the program now is in its 5th edition. So we have also some success I would like to talk to you about. Let's see if this link works. And if you can see it, yep, it appeared. This is a link to a video done by BMAX students. This is Aldin Tralic, who have won an international competition launched by IBM about coding for sustainability. And the idea is to save water consumption. The idea of this app, if you watch the video, you will also see that they explain to you how they use the coding. Okay, so in these pages, now you probably also hear their voices. Okay, and in this page you see really there is an intersection of statistics, because it's a data science, so it's based on data that were available, and coding using this program that was made available for the competition to create then an app that would benefit the citizens. Let's see if we can show it. Okay, here, to monitor daily consumption of water and then have a community sense of whether too much water was consumed or not. So this was a success, as said, as they won then the competition. We also have dedicated BMAX lecture with fantastic scientists. This year we had the participation of the BMAX lecture with Professor Alfio Quarteroni, and we saw numerical analysis concerning the design of Alinghi in the America's Cup competition, and a model that mimics the functioning of the human heart. Thank you very much for being here, and I really hope to be able to see you next year at Bocconi. Thank you very much again, and good luck.